Welcome students, this is Ravi Shankar and today we are going to study about the concept called to be electrostatic potential energy. By studying this electrostatic potential energy, from this we can able to get the expression as well as the definition for the electrostatic potential or electric potential, and also we are going to obtain an expression for electric potential difference. Also we are going to get an expression for electrostatic difference in potential energy. So potential energy difference. So we are also going to study about potential energy difference. A long topic where we are going to state about what do you mean by this potential energy, then potential difference. After getting potential difference, how you can able to get potential from potential energy difference, we have to get electric potential difference. From electric potential difference, we have to get electric potential. Let us see how we can able to get this. So in order to study about this, first of all I am defining in general regarding electrostatic potential energy. First of all, I am going to define. So what is the definition for this? See, in general, we might have studied in mechanics about this potential energy. What is potential energy in mechanics? Work done due to the virtue of its position. Due to change in position, the energy stored in the body called to be potential energy. Similarly, in electrostatics, the potential energy can be defined in terms of work done. See, it was being generally defined as the work done in moving, work done in moving a test charge, or we can say in moving a charge, that is either Q or Q dash, some charge. So work done in moving a charge from one point to another point, one point to another point against electrostatic force, against Coulomb force or against electro force or electrostatic force. Then that work done is stored as potential energy or electrostatic potential energy. This is in general. How you can go this or how you can explain this? Let us go for the explanation as it is given in your book. So let us go for the explanation from where we can able to get the expression. See, in order to consider that explanation, I am considering a diagram. In the R medium, I am considering a point. Let us consider that point as O. At this point O, I am placing a charge plus Q. As we know very clear that if a charge is placed around this charge, you can able to get the influence of the charge, that is nothing but this charge around it produces an electrical field. Let the electrical field produced is called to be E vector. In that electrical field, I am considering 2 points. One of the point, that is the point which is far away, I am considering it as R. The point which is nearer to the charge, I am considering it as P. Let us join this with a straight line. So P2 O2P and P2R. Okay, let us consider this as an axial line or a distance like this. Now I am taking a positive test charge at point R. Let the positive test charge be considered as Q dash, other than unit positive charge, more than that of unit positive charge. Some charge Q dash is being placed at this position R. Very well, you can say in between this charge plus Q and this charge plus Q dash, there is an electrostatic force of repulsion. Let us state that electrostatic force is Fe, or I can say that force is Coulomb force. Both are same or equal, but this is also a positive charge and this is also a positive charge. So I can say a negative charge or a negative force or a repulsive force is said to be available. I can write this in a bold manner like this. That is, see, when you are considering here, I can say it out as what I have set it out as minus Fe. Minus represents what? Minus represents repulsion. Fe represents the electrostatic force. So I can say it out as what? How I can say? I can say it out is equal to minus of Coulomb force Fc. So what I have drawn it here, let us write it out in description. So let us like this. Consider a charge, and that charge is the source charge or the parental charge plus Q, kept at what? Kept at the point O. Now around that charge, when you are considering that charge, then we can say around that charge you are having an electrical field. Let us take it out as E vector. See, in that E vector I am considering a point R. So at the point R, place another charge, place a positive test charge, place a positive test charge. What is that positive test charge? Let us consider it as Q dash. Now let us do one thing. What I have said, this plus Q dash is taken from the point R to the point P. So now this test charge Q dash is taken from or is moved from what point? From the point R to the point P. See, in between this charge plus Q and this plus Q dash, I am having a force of repulsion. If I am moving this charge Q dash from R to P, I have to do a work because already there is an repulsive force. Now I have to move this charge Q dash from R to P, means I have to do a work against the force of repulsion. So I can write, to move the charge Q dash from R to P, work is said to be done. Work is done on what? On the charge Q dash. So a work has to be done on the charge Q dash means an external force should be act on it. So an external force is needed. An external force is required or needed to move the charge Q dash from R to P. That work done is stored on the charge, is stored on the charge as what energy? Stored on the charge as potential energy. See, when you are considering this potential energy is represented as epsilon. You will be writing it like this, U. It is not U, it is called to be epsilon. See, clear? When you are moving this charge plus Q dash from the point R to the point P, a work is said to be done by applying an external force. That work done is stored as the potential energy represented as epsilon. Now you can say the definition. So how you can define? Therefore, I can define the electrostatic potential energy as the work done. Okay, the work done in moving a charge. Here the charge is Q dash. So in moving a charge from one point to another, here against repulsion. So one point to another against Coulomb force or against electrostatic force. So this work done is stored in that charge as what energy? As potential energy. This is called to be the definition. Now let us say, see, I have written it here. An external force is needed to move the charge. So what is that external force? Now we are coming for the next part of this. So therefore, the external force available, I can represent that external force as F external, which is equal to what? This F external is equal to minus of F electrostatic, because the external force applied should be either equal to electrostatic force or it should be equal to Coulomb force, either equal or greater than this electrostatic or Coulomb force. What is this electrostatic or Coulomb force? The charge is considered to be Q dash placed inside the electrical field. So we can say that the Coulomb force is E into Q dash or Q dash into E. Already you have studied E is equal to F by Q. So F is equal to E into Q. Since the force is repulsion, I am saying it as minus of Q dash into E. So if you are knowing the external force, I can calculate the work done. So what is the work done? I can state it out as W. In general, the work done is taken to be F dot S, or I can say F vector dot dr vector or ds vector. Dr vector is the distance moved. Here it is moved from the point R to the point P. So I am putting it like this, integral of, because dr is a small work done. I am going, by integrating it, I am going to get the total work done in moving it from the point or through the distance from R to the point P. So I can say the total work done W is equal to integral of P to R F vector dot dr vector. Now when you are considering this work done is independent of the path, because the force is, the Coulomb force is a conservative force. We can consider like this: since the Coulomb force or the electrostatic force is a conservative force, we can say the work done is independent of the path. Work done is independent of what? The work done is independent of the path. See, we are going to state that Okay, independent of what? Independent of. So when you are considering the Coulomb force, we are saying that the Coulomb force is a conservative force. So therefore the work done is independent of what? Independent of the path along which the charge is carried or the charge is moved. Then what it depends upon? But the work done depends upon. But the work done depends on 2 points, the initial and the final point. So, but we can say the work done depends on the initial and the final point. Initial and the final point. So, we can state again. See, we have calculated the work done as the potential energy, the work done in moving the charge from one point to another point. Here we have taken the charge as Q dash from one point to another against the electrostatic or Coulomb force is called to be the electrostatic potential energy represented by epsilon. For doing this work, external force is necessary. The external forces we can state as F external, which may be equal to or greater than the Coulomb force or the electrostatic force. So I am writing it as F electro or F Coulomb. Since it is repulsive, I am representing it as minus. What is its value? The value is E Q dash or Q dash E. Because inside the electrical field, at a point, the charge Q dash is placed. So the force experience is given by E Q dash, since E is equal to F by Q. Since it is repulsive, I have introduced the negative sign. In general, we can say work done is equal to force into distance. By considering a small distance dr, I can say work done as dw. On integrating it, I will be able to get the total work done w. So w equal to integral of r2p f vector dot dr vector. Now, when you are considering this work done is independent of the path. Why? Because the Coulomb force is a conservative force. But on what factor this work done depends? This work done depends on the initial as well as the final point. Now, let us go for the potential energy difference. How? I think you hope you should be clear with this idea. Now, what I am going to do? Now, what I am going to consider is, I am going to consider the potential difference. See, I have taken 2 points, isn't it? One is R, another one is P. So, what I am considering it as let. Okay, let us take like this. Let the potential energy associated with at the point or associated with the charge Q dash, at the point R. I am representing it as epsilon R. Similarly, let the potential energy associated with Q dash at the point P, I am considering it as epsilon P. Now, I am going to calculate the difference in potential energy at the point P and at the point R. Then, the difference in potential energy is defined as the work done in moving or in bringing the test charge. Let us consider here the charge Q dash from the point P to R or from R to P. Since minus So the nearer value will be having a higher value, higher magnitude. So from P to R is given as, or is given by. How you can able to get? So I can get this work done as, work done is equal to epsilon P minus epsilon R. From greater magnitude, I have subtracted the lesser magnitude. Here, it is considered to be the difference in potential energy. Since it is the difference in potential energy, I am writing this as is equal to delta or D. I can say delta of epsilon. So this I am considering it as change in potential energy, or the difference in potential energy taken to be the work done. Again I can write delta epsilon is equal to, what is the formula? Here F, or I can say F external multiplied it with the distance. The distance mode is dr, or I can say it out as dr vector. I have to integrate from what position to what position I have moved. I have moved it from the point R to the point P. So substitute and again simplify this. As we know, F external, since F external is equal to, already in the previous step I have written it, minus of F Coulombic force, or minus of F electrostatic, which is equal to minus of E into Q dash. Take this and substitute it here. You can able to get as, therefore I can state change in potential energy delta delta epsilon is equal to integral of R to P. Then what is this value? This value is minus of Q dash into E vector multiplied it with what the distance. What is the distance? This multiplied means it is the dot product into dr vector, which is equal to, see, Q dash can be taken as a magnitude. So Q dash integral of R to P, the direction for E is minus, so I can say it out as minus E vector dot R vector. This we are calling it out as the expression for what? Expression for the change in potential energy when you are moving the charge from one point to another point. See, from this change in potential energy, okay, we are stepping up to the next concept. Here we have calculated, this gives, or I can write here, this expression, okay, this expression gives potential energy difference. Potential energy difference. Now I have to go for potential difference. See, from potential energy, still I am writing here. See what we are going to get from potential energy difference. We are going to get potential difference. Both are different. So what do you mean by this potential difference? In general, we will be calling this potential difference as voltage. If you are taking a battery, see, at one battery means I am saying about a cell, at a cell, 2A or AAA cell. At one end you will be having positive, that is positive potential. At the other end you will be having negative potential. Difference is voltage, that is the potential difference. See, simply I will be drawing it here. You just consider a battery cell. See, when you are considering a AA or AAA battery cell, here you will be having the terminal considered to be positive. Here you will be taking it as negative. Here it is taken to be what? Here it is considered to be positive. See, this is positive. and this is negative. Difference in between the two, in a battery it will be equal to 1.5 volt. This is the potential difference, commercially known as the voltage. Where or how you can able to get that potential difference from this potential energy difference? See, we know that. Let us again write what we have derived in the previous case. We know that change in potential energy is equal to Q dash integral of R2P minus of E vector dot dr vector. This is potential energy difference. Now you calculate potential energy per unit charge. Potential energy per unit charge means nothing but change in potential energy divided by the charge Q dash. You take this Q dash and divide it here. This potential energy per unit charge gives rise to potential difference. Clear? So potential difference is defined as potential energy per unit charge. Okay, so therefore I can say potential difference is equal to, change in potential energy per unit charge. So I am saying it as like this: change in potential energy per charge or per unit charge. Or you can say change in potential energy is delta epsilon divided by, here the charge available is Q dash. So delta epsilon divided by Q dash will be giving you potential difference, and that potential difference is represented by change. I am representing it as delta and the potential difference represented as V. Clear? Very important concept. You can very well or easily you can have it in your mind as potential difference or difference in potential called to be voltage. Consider to be change in potential energy per unit charge. So I can get this equation. So how I can write this now? I can write this as, therefore delta V, I am saying it as potential difference. This potential difference delta V is equal to potential energy per unit charge, which is equal to, what is that value? Integral of R2P minus of E vector dot dr vector. And this change in potential energy is measured in terms of an unit called to be volt. I think you will be very clear with this. See, let us mark it out. See, potential difference is defined as the potential energy per unit charge. Nothing but change in potential energy is delta epsilon divided by Q. Here also you can say this equation is independent of Q dash. This is considered to be Q dash. So delta U by Q dash. So the above equation we can write like this: the above equation is independent of the charge, Q or Q dash. See, this equation, okay, I am writing this, that is, therefore this equation I am writing the quantity, which, what is that quantity? Delta epsilon divided by Q dash, which is equal to integral of R2P minus of E vector dot dr vector, is called as electrostatic potential, is called as electrostatic potential, is otherwise called to be electrostatic potential. See, now from this electrostatic potential we have to define. how to define. Let us write the definition. So, definition can be written as, see, the work done by the external force, work done by the external force in moving a unit positive charge and unit positive charge from one point to another point R. We can write from R to P against the force of repulsion, or against the electrostatic force of, against the Coulomb force, or against the electrostatic force. Here it is repulsion. Here it is repulsion. The electrostatic force is repulsion. See, we can also denote that as, it can be denoted as, see, change in potential difference is delta V is equal to potential at the point P minus potential at the point R, Vp minus Vr, where we can write, what is this Vp? See, later stage I will be defining what is this Vp. Vp is potential, electric potential at point P, at the point P. And what is Vr? Vr is, we can say, the potential at the point what? Potential at the point R. Now, when you are considering this delta V, that is Vp minus Vr, how you can write again? Therefore, combining this with the previous equation, we can write delta V is equal to Vp minus Vr is equal to integral of R to P minus of E vector dot dr vector. See, all these expression giving you the expression for the potential difference. See how you can write this. From this I can able to get, this is called to be potential difference. See how I can able to get electric field from this, or electrical potential energy from this. Therefore, I can write the electric by cross multiplying. See, this can be written as, what is this delta V? Change in potential difference, change in potential energy per unit charge. By cross multiplying, you can able to write potential energy. So, therefore, the electric potential energy, can also be written as electric potential energy can be defined in terms of, electric potential energy can be defined or can be written as the product of, written as, see, electric potential energy is change in delta epsilon is equal to, on cross multiplying, so product of change in potential, so potential difference multiplied with the charge mode. So this is also another definition by which the electrical potential energy can be what? Electrical potential energy can be defined. See, from this I can able to get what? From these two equations I can able to get what is this potential at the point P, or what is the potential at the point R. So in order to define the potential at a point, now what we have defined is potential difference between 2 points, or done in moving a unit positive charge or a test charge from one point to another. But we have to define what is the potential at a point. I am writing how to calculate, how to calculate or how to define potential at a point. I have written that Vp VR. What is that? Potential at a point P or potential at a point R. So how to define potential at a point? Let us take this equation again. See, we know that delta V is equal to Vp minus VR. See, in this case, the work is said to be done by moving that unit positive charge from the point R to the point P. Instead, you consider like this: if or suppose the point R, suppose the point R is taken at infinity, What do you mean by this? See, look at the diagram. Here, first of all, we have taken the point O, where we have placed the charge. From this, at a particular distance, I have placed the point P. Here I have taken the point R, isn't it? Now this point R is taken away from this electrical field and it is somewhere taken toward, it is somewhere taken to some infinite position. See, if it is taken to some infinite position means, okay, if I am taken it to some infinite position means, this point is not under the influence of this electrical field produced by this charge. If it is taken away, if it is taken at infinity, then potential at the point infinity, which is equal to potential at the point R, is equal to 0, because this point is not having the influence of this electrical field. Okay. See, this positive charge is having no influence of this point because it is taken away or out of the electrical field. So I am saying V infinity is equal to VR, which is equal to 0. Then you take this value and substitute in this above equation. What you will be able to get when you are substituting in this equation? See, substituting for VR in this equation, that is delta V, substituting, clear? Substituting for VR as 0, we get potential difference delta V is equal to Vp minus 0, that is equal to Vp. What is this Vp? Vp is nothing but potential at point P. So how you can define now? Then we can say that. How you can define now? Then we can define, okay, then we can define potential at a point P, or we can say potential at a point is given as the work done in moving, and unit positive charge or test charge, unit positive charge or test charge, from where we have moved, from the point R, which is at infinity, from infinity, okay, from infinity to the point P, to the point is P inside the electrical field, and I am doing it against electric force or against Coulomb force or against electrostatic force. Here the electrostatic force is repulsion. This we are calling it out as the definition for the potential at a point. So the potential at a point is defined as, how we have defined, you see, the potential at a point is defined as the work done. What it is the work done? The work done in moving an unit positive charge from where I have moved from infinity to the point P inside the electrical field against the electrostatic force of repulsion. So this considered to be, we can state like this: work done in moving an unit positive charge or test charge from infinity to the point P against the electrical force inside the electrical field, inside the electric field E vector, inside the electrical field E vector is called to be the potential at a point. Very, very, very important definition. Now, how you can write this mathematically?